Welcome to Data Science with EJD. In this video, we continue with dimensionality reduction techniques under unsupervised learning, under machine learning. And we go on to another method, another technique called uniform manifold approximation, UMAP. For dimensionality reduction, we've seen PCA, we've seen PCA power component analysis, I believe, and then we've seen t-SNE, which is um, T distributed SNE. I've forgotten what that S is. S neighborhood embedding. I'm trying to remember what that S is now. Okay, let me quickly check. It should be something pretty simple. t-SNE. Yeah, yeah. T distributed stochastic neighbor embedding. Right. Okay, so here focus is on UMAP, uniform manifold approximation. So let's look at some aspects of this. So the full name, of course, is uniform manifold approximation and projection. That's the full name. So that's where the UMAP comes from. So uniform manifold approximation and projection. Then the purpose is non-linearity dimensionality reduction. Just like, PCA is linear, t-SNE is non-linear. Now UMAP is also non-linear. So it is a non-linear dimensionality reduction, embedding high dimensional data in low dimensions for visualization or processing or pre-processing. Now the whole idea is you have data in 4 dimensions, 5 dimensions, and upwards, and then you're bringing them down into 2D or 3D. So the core idea is that it assumes the data lies on a Riemannian manifold and approximates it by constructing a graphical representation, which is like a fuzzy topological structure, and then optimizes a low dimensional embedding to preserve that structure. That's the idea of uniform manifold approximation and projection, UMAP. The mathematical basis is the manifold theory and topological data analysis, which is simplicial. I'm talking about simplicial complexes, and of course, fuzzy set theory. So, manifold theory, topological data analysis, and fuzzy set theory. And the key authors of UMAP are Leland McInnes, John Healy, and James Melville, and in their paper published in 2018. The implementation is available in the UMAP Learn Python package. All right. Why use uniform manifold approximation and projection? The advantages: it is fast. Interestingly, it's much faster than t-SNE, especially for large data sets. It can handle millions of samples. Then it is scalable. It has low computational and memory overhead. Then it preserves local and global structure because it balances neighborhood faithfulness and global geometry. Then it has reusable embeddings because it supports the transform on new or unseen data. Then it is flexible because it is good for both visualization and dimensionality reduction before machine learning tasks. The use cases, you can use it for exploratory data analysis and visualization in 2D or 3D plots. It is good for noise reduction, for feature engineering. It is good for preprocessing before clustering or classification, and embedding for large-scale machine learning pipelines. Now, comparing UMAP and t-SNE, UMAP, uniform manifold approximation and projection, versus T-distributed stochastic neighbor embedding. Comparing the two of them, since they're both non-linear dimensionality reduction techniques, let's see. Talking about speed, UMAP is fast, t-SNE is slow, particularly because it has quadratic time complexity. Then the scalability, UMAP handles large data well, while t-SNE is poor for large data sets. Then aspect, it preserves global structure. UMAP preserve global structure better than t-SNE, which is weak, and t-SNE is good only at local clusters. Like that. Then embedding new data, UMAP, it's possible to embed new data in UMAP, and embedding new data is not possible in t-SNE because you must rerun the whole thing. Then for parameter intuition, UMAP has clear, you have n neighbors minimum distribution. Then t-SNE more sensitive to perplexity. The reproducibility, UMAP is more stable, while t-SNE is more stochastic, gives more stochastic results. For output, you have embedding in 2 dimension or 3 dimension or even higher in UMAP, but in t-SNE it is typically only 2D or 3D for visualization. So let's talk about key parameters in uniform manifold approximation and projection, UMAP. So talking about n neighbors, this controls local neighborhood size. Larger is equal to more global structure. So the larger the number of neighbors, the more global the structure. And the typical number of neighbors is 5 to 50. The minimum distribution, mean underscore dist. It controls how tightly UMAP packs points together. Lower means tighter clusters, typically zero point 0.0 to zero point 0.5. Then end component, that talks about output dimension. So you can use 2 or 3 for visualization, higher for general dimensionality reduction. So the metric, it's a distance metric for UMAP. Yeah, it can be Euclidean distance or cosine distance or something. So an example, since so we can look at a systematic Python implementation. Below is a complete Python script that loads a data set, standardizes the data set, reduces dimensions using UMAP, reduces dimension using t-SNE, plots both embeddings side by side for clear comparison. Of course, we need to install the dependencies, the things you need to run in this case. You need to install UMAP-len. That's a library of its own. Uh, yeah, UMAP-len, and then you have scikit-learn, you have matplotlib seaborn. I mean, we've been using the rest before. The new thing here is umap.learn. So I've run it before, so it's just going to, okay, first of all, let me go and get, I keep forgetting to put the line numbers because that's easier to refer to, yeah. Okay, so now I want to run this, especially the UMAP dash len. So it takes a bit of time because I've done it before. If you're doing it for the first time, it may take so much time. It may take more time than this actually. And then to load the required libraries now. So you import UMAP from sklearn.manifold, import t-SNE, dataset, you are loading the digit dataset. You know, we used the digits dataset yesterday. It's pictures of handwritten digits, okay, which we've been using since the last video or so. Then we have the standard scaler for preprocessing. Then we have matplotlib and seaborn for for visualization, and we have time to want to check time as we do this. So we run this. The start tells you it's working. It's still on, but once a number shows, then it's done. Okay, taking a bit of time. So still on that. Okay. Um I think it's longer than usual. By now, it should have been done, but wait, okay, done. So in step 3, we want to load and preprocess the data. So load example data digits. We have 1,797 samples and 64 features. All right. So the digits is equal to load digits. Then X is digit dot digits. Y is digit dot target. Of course, in this case, we don't need the target because we are dealing with unlabeled data. We only have the inputs. From the inputs, in supervised learning, we have inputs or features and outputs or targets. But here we just have inputs. All we are doing is to discover patterns from the input, right? So we are only interested in the X here. So then you also standardize the features because it's always necessary in this case. So that is done easily. Then you now want to run UMAP, that's uniform manifold approximation and projection. So you want to create a UMAP model. You have UMAP underscore model equals UMAP. So it means this big capital UMAP is a library or function inside of the UMAP itself, inside the UMAP library. So number of neighbors is 15. So we have local neighborhood size. Minimum distance is 0.1. You know, we can have 0 to 0.5. So this tells us how tightly to pack points. Then end component, that's output dimension, that's 2. And the metric is Euclidean. So we want to measure the time this takes. So we start underscore UMAP. So time dot time. X UMAP now is equal to UMAP underscore model dot fit. These where we train the model with the data, and then end UMAP time dot time. So the time it takes to finish up, and then we want to know end map minus end map end UMAP on minus start UMAP, the number of seconds that takes that we measured for us. So okay, that it's gonna take a bit of time for sure. So we patiently wait until the number is outputed. So we know the time it takes to when it starts. Yeah, so this one takes 13.95 seconds. If I do it again, it's likely going to take maybe something different from 13.95. Yeah, it's 2.89, right? Let me take it another time. So, it keeps changing. This is 2.83. Okay, like, is it like converging? Let me see. 2.83. If you have something to Now 2.96. So it keeps going like that. Now, the next thing we have run UMAP. Now we want to run t-SNE, which we did in the last video. So create t-SNE model. So we go about the same thing. So t-SNE model, t-SNE, end component to random states to ensure reproducibility. So we don't expect this one to change time or something like that. Let's see how if that's true. Perplexity is 30, learning ratio is auto. Then you also measure the time just like we did for UMAP. So we do that and see what the time looks like. Okay, taking a bit of time. Start underscore t-SNE is time dot time. Yeah, that takes 11.04 seconds, more than UMAP. So you can see UMAP is faster, like we said previously. t-SNE is comparatively slower than UMAP, you know, like that. Great, 10.72. Okay, like the time is getting smaller now, you know. But of course, even at that, the UMAP did not get beyond 2.96, I think. Didn't it get to 3? But this now it's 11.02. So obviously, UMAP is faster than this, than t-SNE. Now I want to visualize both embeddings, right? So plot UMAP and t-SNE side by side. So we say plot dot figure. The figure size is 14 by 6. So we do subplot 1, 2, comma 1. So we have one row, two figures side by side for sure. So in one row, so SN is the scatter plot, X map, Y is X map and all that. Here is Y, blah blah blah, all these things. So the same for t-SNE, we go like that. You can read that better to understand. Okay. So now we have it in a jiffy. So you can see the t-SNE projections looks like uh maybe given the world map C kind of thing. Uh but then for UMAP is not that crowded like that. Let's see what happens. What do we observe in these situations? Right? For the clusters, both UMAP and t-SNE reveal clear digit clusters. So we have digit clusters in all of these places, right? But then separation, UMAP often maintains slightly better global positioning. So you see the positionings are more distinct here compared to here. So it's more like things are more all over the place compared to UMAP. Then the speed, UMAP runs faster than t-SNE on larger data sets. Now we've already seen that before. So while UMAP is just something close to 3 seconds, t-SNE is over 10 seconds for sure. Then speed, UMAP runs faster. Okay, we've said that already. Reusability, can the UMAP model transform new data to embed new points? t-SNE does not allow this, just like we see before, right? And the question is this: when do you use UMAP and when do you use t-SNE? So when you have large data sets greater than 10,000 samples, UMAP is recommended. When you need to transform new data, UMAP is recommended primarily for visualization of very small data. If you have very small data or you just want to visualize. So either is fine. t-SNE may reveal fine local details. So embedding for machine learning pipelines, UMAP does it. So you see UMAP has a lot of advantage, a huge, massive advantage over t-SNE. So the key takeaway here is that UMAP is a powerful modern tool for visualizing and understanding complex high-dimensional data sets efficiently, making it a go-to choice for large-scale exploratory data analysis and feature compression in modern machine learning pipelines. So we have some references. The UMAP paper by McKinsey et al. In 2018, and we also have UMAP Learn on GitHub, like that. So you see the whole thing on GitHub here. Uniform manifold approximation and projection. We have it on there. Okay. Then we also have t-SNE paper. Okay, we referred to that yesterday, like where we talked about Hinton, who is seen as one of the fathers of artificial intelligence, right? Okay, you can click on that. It takes us straight to the paper. Lawrence van der Marten and Jeffrey Hinton, right? Then the UMAP paper, let's see that. Okay, it's on archive. UMAP Uniform Manifold Approximation Projection for Dimension Reduction by Dylan Markins, John Haley, and James Melville. Okay, that's all there is to this video. Thank you so much for listening. Let me know if there's something you'd like me to try out or you know whatever. If you have subscribed already, I thank you so much for that. If you have not subscribed, of course, you'll be missing a lot. So go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. On my channel, you can be a member. You can click on join to see the possibility of membership you can be part of, the possibilities, and you can see the perks attached to each of those, right? So feel free. avail yourself of all these privileges as much as you can. But if all you do is subscribe, that's good enough. That's fine, right? Be sure to like and share also so that more people can have access to this great content I have going on here. Till I come your way again, keep doing data right. Bye.